Hello everyone. So in this video I'm going to cover electromagnetic induction and alternating current. So I have categorized previous year's JEE Mains questions as 12 problem types. If you master these 12 types, you'll be able to answer both the questions which is going to come in JEE Mains. So let us see who will get benefited from this video. So you know basics, your NCERT level knowledge is fine and you have done some coaching, but you are struggling with the problem solving part. So this video is for you. And how you can watch this video effectively: first you have to revise the short notes which you have prepared for this chapter, then write down any important information which you come across while watching the video, and whenever I discuss any illustration you have to pause the video, try to solve the question on your own. Right, so if you look at the syllabus, this is the syllabus. You can pause the video and just look at the syllabus, and this is the mind map for electromagnetic induction, and this is the mind map for alternating current. Just have a look at it to see the linkages in different topics. Now let us see the very first problem type, and it is based on Faraday's law. So here the induced EMF in a closed loop will be given as minus d phi by dt, where d phi by dt is the rate of change of magnetic flux. Now let us see the application based on this formula. A rectangular loop of length 2.5 meter, width 2 meter is placed at 60 degree to the magnetic field of 4 Tesla. So this is L, and this will be breadth, and this is the angle. So I'm assuming this angle is the angle between the area vector and the magnetic field. So if this is the area, and this will be the area vector, and this is magnetic field, so I'm taking this angle as theta. So we can say the induced EMF. So the loop is removed from the field in 10 seconds. The average EMF induced in the loop during this time. So EMF induced will be minus d phi by dt. Or since we want to find the average value, we'll find the change in the flux in that duration. So it can be written as minus b a cos theta, or you can say delta b a cos theta divided by delta t, right? So delta b can be written as final minus initial. So final is 0, initial is 4, and area will be 2.5 times 2, and cos 60 is 1 by 2 divided by the duration, which is 10 seconds. So this comes out to be positive 1 volt. So the EMF induced will be 1 volt. So option 3 is the right answer. Now let's see the next question. A square loop of side 10 centimeter and resistance 0.7 ohms is placed vertically in the east-west plane. Right, so let me show here. This is west, this is east, and this is north, and this is south. And we have given a square loop which is placed vertically. Side is given as 10 and the resistance is 0.7 ohms. A uniform magnetic field of 0.2 Tesla is set up across the plane in northeast direction. Now there is a magnetic field which is in northeast direction. So in this case we can say the area vector will be towards north. So that will be the area vector. So the angle between the area vector and the magnetic field will be 45 degrees. The magnetic field is decreased to 0 in 1 second. So we know delta B, right? That will be 0 final minus initial. And initial field is 0.2 Tesla in 1 second. So delta B by delta T is 0 minus 0.2 by 1. So it comes out to be 0 minus 0.2 Tesla per second. And we have to find the magnitude of the induced EMF, which is given as root x times 10 raised to power minus 3 volts. So we can say induced EMF will be, in this case, delta B by delta T times the area times cos 45 degree with a negative sign. So minus of minus 0.2. Area is 10 square centimeters, so it will be 0.1 square, and cos 45 will be 1 by root 2. So let us simplify this. So this can be written as 2 times 10 raised to power minus 3 divided by root 2, and it is nothing but root 2 times 10 raised to power minus 3 volts. Now if you compare our answer with the given thing in the question, x comes out to be 2 only. So 2 is the answer of this question. Now let us see the next question. The magnetic flux linked with a closed circuit of resistance 8 ohms varies with time as, so we have given instantaneous flux, the induced current in the circuit at time 2 seconds. So since we have given phi, with the help of phi we can find the induced EMF. So phi is given as 5t square minus 36t plus 1. So d phi by dt will be equals to 10t minus 36. And we have to find the induced current at t equals to 2 seconds. So we can say the magnitude of the induced EMF will be 10t minus 36, and its value at t equals to 2 seconds will be 10 times 2 minus 36, which comes out to be 16 volts, right? Now we know the EMF induced. Now what is the induced current? So induced current will be induced EMF divided by the resistance. Now what is the resistance? 8 ohms is the resistance. So 16 divided by 8, so it comes out to be 2 ampere. So 2 ampere is the induced current. Let us see the next question. A coil is placed perpendicular to the magnetic field of 5000 Tesla. So if this is the coil, this is the area vector, and the magnetic field is in this direction only, right? So that what they mean, that the coil is placed perpendicular to the magnetic field. So the plane of the coil is perpendicular to the magnetic field. So magnetic field is this, and the area vector will, both are parallel. When the field is changed to 3000 Tesla in 2 seconds, so field is changing from 5000 Tesla to 3000 Tesla in 2 seconds. So from this we can find the rate of change of magnetic field. An induced EMF of 22 volt is produced in the coil. So we can say EMF induced will be minus of, that will be field is changing, so area times delta B divided by delta T, right? And the cos of 0 degree. So what is the area? Area is given as, diameter is given, so we can write this as pi 0.01 square, so that is the area, and delta B will be 3000 minus 5000, and delta T is given as 2 seconds. Cos 0 is 1, so that will be minus 22 by 7 times 10 raised to power minus 4, and this will be 2 with a negative sign, 10 raised to power 3 by 2, right? And we have to find the number of turns. Okay, right? So there are number of turns also, so there has to be n also, right? And E is given as 22. So this 22 will get cancelled out, and this negative will cancel out this negative, so we get n as 70. Okay, so 70 is the number of turns. So option 2 is the right answer. Now let us see the next problem type, and it is based on motional EMF. Now let us see the different types of question that can be asked. If there, suppose magnetic field is into the plane, and there is a conductor of length L, and let us this end is P and this end is Q, and this conductor is moving in the right direction with the uniform velocity V, then there will be an induced EMF. So in that case, the top end will be at high potential, bottom end will be at low potential, So induced EMF will be given as BLV, where B is the magnetic field, L is the length of the conductor, and V is the velocity. So all these three are mutually perpendicular to each other. But if we have given a conductor which is rotating, let us say this case. There is a conductor of length L which is rotating with an angular velocity omega. So in this case, the induced EMF, so this end will be at high potential and this will be at low potential, and the induced EMF will be half B omega L square. Okay, so we're going to use these two formulas, and this is known as motional EMF. Now let us see some of the illustration. So a ceiling fan having three blades of length 80 centimeter, each is rotating with an angular velocity of 1200 rpm. The magnetic field of the earth in that region is 0.5 Gauss and the angle of dip is 30 degrees. Okay, let me just quickly tell you what is angle of dip. So angle of dip is the angle made by the net magnetic field at a place with the horizontal. So if this is the horizontal plane, which is basically the magnetic meridian, so magnetic field is in this direction, which is given as 0.5 Gauss, and 1 Gauss is 10 raised per minus 4 Tesla. So we can say magnetic field is 5 into 10 raised per minus 5 Tesla. So this is B, and this angle is given as angle of dip, which is 30 degrees. And we have given a ceiling fan, and obviously the ceiling fan blades are rotating in a horizontal plane. And if you want to find the induced EMF across the blades, then you have to consider magnetic field component which is in the vertical direction. So if I show the ceiling fan, right? So this is the ceiling fan which is rotating in a horizontal plane. So we have to consider magnetic field which is vertical. So if you take the component of this magnetic field, so there will be a vertical component which is BV, and there will be a horizontal component. So horizontal component is not responsible for any induced EMF. So vertical component is responsible. So we can say BV is nothing but B sine 30 degrees. And B is given as 5 into 10 raised per minus 5 Tesla. Sine 30 is 1 by 2. So that will be 2.5 into 10 raised per minus 5 Tesla. Now since each wing of the fan is rotating and the length of each blade is 0.8 meter, so we can say the EMF induced between the center and the edge of the wing will be half B omega L square. So this will be half, and this B is nothing but BV, right? And BV is 2.5 into 10 raised per minus 5. Omega is given as 1200 rpm, so this can be written as 1200 times 2 pi by 60. So this will give us rpm in radians, or angular velocity in radians per second, multiplied with square of the length. So it will be 0.8 square. So let us simplify this. So this will give us 20. This 2 will get cancelled out. So we have 5 by 2, or we can say this will become 50 times 10 raised per minus 5 times pi times 64 into 10 raised per minus 2. And we have to find the value of n, right? So this is given as n times pi times 10 raised per minus 5, so which is equals to 50 times 64 pi times 10 raised per minus 7. Right, so pi will get cancelled out. So n comes out to be 50 times 64 times 10 raised per minus 2. So which is 32. So n comes out to be 32. So that is the answer. Now let us see this illustration. A rectangular loop of side 12 centimeter and 5 centimeter with its sides parallel to the x-axis and y-axis respectively moves with a velocity of 5 centimeter per second in the positive x direction. in a space containing a variable magnetic field in the positive z direction. Okay, let me draw the diagram first. So we have given y-axis, this is the x-axis, and there is a loop, and the sides of the loops are parallel to x and y direction. Something like this. Okay, it can be anywhere, but the side should be parallel to x and y direction. The length of this loop is given as 12 centimeter, and the breadth is given as 5 centimeter. And the magnetic field is in the positive z direction. So magnetic field is in positive z direction. Something like this. Okay, and the magnetic field is everywhere. And what we have given, the field has a gradient of 10 raised to the minus 3 Tesla per centimeter along the negative x direction. So what does it mean? So if you are going in the left direction, if you travel a distance of 1 centimeter in the left direction, magnetic field will increase by 10 raised to the minus 3 Tesla. And it decreases with the time at a rate of 10 raised to the minus 3 Tesla per second. And this magnetic field is also changing with time. So if the resistance of the loop is 6 milliohms, the power dissipated by the loop as heat is dash times 10 raised to the minus 9 watt. Okay, so here the EMF is being induced due to the change in the magnetic field with space and due to the change in magnetic field with time. So we have to find the EMF induced by both the ways. So let us first find the EMF induced due to the change in magnetic field due to space. So let me call this as E1. So this will be EMF induced due to change in B or magnetic field with space. Right, so and we have given this loop is moving with a velocity of 5 centimeter per second in the right direction. So if the magnetic field is out of the plane, loop is going in the right direction, we can say there will be no EMF induced in the horizontal sides. Is it clear? Because these sides are parallel to the velocity. But if you look at the vertical sides, the field at the left side will be more than the field at the right side. So we can say, let me name it. So if this is P and this is Q, R and S. So if you look at PS, it is going in the right direction and field is out of the plane. So we can say bottom end will be at high potential, above end will be at low potential. Right? So let us say the EMF induced is E1, or you can say in this case will be EPS. So this can be written as magnetic field at PS times length, which is given as 5 centimeter, times velocity, which is 5 centimeter per second. Similarly, if we consider side QR, again it is going in the right direction, right? So in this case, the bottom end will be at high potential, top end will be at low potential, and let us call this EMF as EQR. So this will be magnetic field at QR times 5 centimeter times 5 centimeter per second. Okay, so we can so if we take magnetic field at QR, so if magnetic field at QR is B, then magnetic field at SP will be B plus 10 raised to power minus 3 times, what is the length? 12 centimeters. So if we go by 12 centimeter in the left direction, the field will increase by 12 times 10 raised to power minus 3 Tesla. Okay, now since these two EMF. So here we have EMF polarity like this. Here we have EMF polarity like this, and these two EMF are opposing each other. So we can say E1. Let me write here. So E1 will be, and which will be stronger? The left one will be stronger. So we can say it will be EPS minus EQR. So that will be 25 centimeter square per second times the difference, and difference is nothing but 12 into 10 raised per minus 3. So this can be written as 25 times 12 will be 300, so this will be 0.3 times 10 raised per minus 4 volts, right? So if you want to find the EMF induced due to the change in the magnetic field, so what we can say, at a particular time, if you want to find, E2 will be area, that will be 12 times 5 into 10 raised per minus 4, area times the rate of change of magnetic field, so dB by dt. So dB by dt is given as 10 raised per minus 3 Tesla per second. So it will be 60 times 10 raised per minus 7. So it comes out to be 0.06 into 10 raised per minus 4. Now we got, if we add these two EMFs, we'll get the total EMF induced in this loop. So we can say the net EMF will be 0.36 into 10 raised per minus 4 volts, and we have to find the power dissipation. So power dissipation will be E net square by R. So that will be 36 times 36 times 10 raised to per minus 12 divided by R, which is 6 into 10 raised to per minus 3. So that will be 6. So it will be 216 times 10 raised to per minus 9 watt. So if you look at the the blank here, it should be 216, right? So that is the answer of this question. Now let us see the next question. A horizontal straight wire 5-meter long extending from the east to west, falling freely at right angle to a horizontal component of Earth's magnetic field. Okay, so let me draw here. So this is west, this is east, and this is north, and this is south. So the horizontal magnetic field will be from south to north, and there is a wire which is falling vertically, which is aligned from east to west, and its length is 5 meter. So the instantaneous value of EMF induced in the wire when its velocity is 10 meters per second. Now if in this particular case, this wire, this conductor is cutting the magnetic field line, so there will be a motional EMF, so which will be BLV. So magnetic field is 0.6 into 10 raised per minus 4. Length of this conductor is 5 and the velocity is given as 10. So this comes out to be 3 into 10 raised per minus 3 volts. So 3 is the answer of this question. Right, so let us see the next question. A square loop PQRS having 10 turns and area is 3.6 into 10 raised per minus 3 square meter and resistance is 100 ohms, is slowly and uniformly being pulled out of the uniform magnetic field of magnitude 0.5 Tesla. Work done in pulling the loop out of the field in 1 second is dash times 10 raised to minus 6 joules. So we have to find the work done. So what we can say, since we are moving this uniformly, so whatever work which is being done by the external agent will be dissipated in the form of heat energy, because we are not changing the kinetic energy of the loop. So we can say work done by external agent will be equals to heat dissipation, right? Rate of heat dissipation. Let me write it as rate of heat dissipation. Or joules heating, right? Right, so what we can do now, first we have to find the EMF induced. So when we are pulling this out of this magnetic field, this PS section will not be in the magnetic field, so there will be no EMF induced in PS section. So we are left with only QR, and QR is moving in the left direction. So we can say there will be polarity. So V in this direction, this will be at high potential, this will be at low potential. So there will be a EMF induced. So this EMF induced will be BLV, and B in this case is zero 0.5. Length is length is given as uh, area is given, right? So if area is given, we can also find the length. It will be root of 3.6 into 10 raised per minus 3, which is 6 into 10 raised per minus 2 meter. So 6 into 10 raised per minus 2 meter. So B L V, and the velocity is, since it is moving uniformly and it covers a distance of 6 into 10 raised to minus 2 meter in 1 second, so the speed will be 6 into 10 raised per minus 2 divided by 1. So that is the EMF induced, and resistance is also given, so we can say the power dissipation will be E square by R. So let me simplify this, so that will be 18 into 10 raised per minus 4. So square of that, 18 times 10 raised per minus 8 divided by the resistance, which is 100. So this comes out to be 324 times 10 raised per minus 6. 324, okay, let me again check, minus 4 BL. Yeah, number of turn I forgot to add, so there will be number of turns also. N is also there, times N times N square, right? And N square will be what? N square is 100. So this comes out to be 324 times 10 raised per minus 4, which can be written as 3.24 into 10 raised per minus 6 joules. So if you compare, the answer will be 3.24. Since it's an integer type question, so the answer will be 3. So we'll round off this 3.24 as 3. So 3 is the answer. A square loop of side 15 centimeter being moved towards right at a constant speed of 2 centimeter per second as shown in the figure. The front edge of edge enters the 50 centimeter wide magnetic field at t equals to 0. The value of the induced EMF in the loop at t equals to 10 seconds. So at t equals to 10 seconds, let us see the position of the loop. So in 10 seconds, it will cover a distance of, speed is given, na? Speed is 2 centimeter per second. So that will be 20 centimeter. So if the loop was here at t equals to 0, so it will cover 20 centimeter and its side is 15. So it will be inside. Can you see this loop is completely inside the magnetic field and there will be no change in the flux in this loop. So we can say the EMF induced will be 0. So option 2 is the right answer. Now let us see next question. A rod of length 60 centimeter rotates with a uniform angular velocity of 20 radians per second about its perpendicular bisector. In a uniform magnetic field of 0.5 Tesla, the direction of the magnetic field is parallel to the axis of the rotation, the potential difference between the two ends of the rod. Okay, let me draw the diagram. So magnetic field, let us say it is into the plane, and there is a conductor which is rotating about its axis of symmetry. So it is rotating about, say, this axis. So in this case, if we consider, and let us say the angular velocity is anti-clockwise. So if we consider left part, in this case the EMF induced will be what? So this end will be at high potential and this will be at low potential. So let us say this EMF is E, right? And this E will be half B omega L by 2 square. Similarly, if I consider other half, let me show that with the red color. This other half, in this case the EMF induced, the polarity will be like this. So the left end will be at high potential, right end will be at low potential. And by symmetry, this EMF is also E, right? So if this point is O, this point is A, and this point is B, so we can say VO minus VA is E, and VO minus VB is E. So from this, if we can say VA is equals to VB, and we have to find the difference, potential difference between the two ends of the rod. So we can say it will be 0. So VA minus VB is 0. So it should be 0, right? Now let us see the next problem type, and it is based on inductors and self-inductance. So what are inductors? These are basically the solenoids. If you set up some current in the solenoid, it behaves like an inductor. And what is self-inductance? So let us see. If there is a inductor, and through this inductor, let us say the current is changing as di by dt, then there will be a EMF induced, and let us say this di by dt is positive, then left hand will be at high potential and right hand will be at low potential. So the potential drop will be L times di by dt, where L is the self-inductance. But if the current is decreasing, the polarity will reverse. So this will be negative and this will be positive. Again, the magnitude will be L di by dt, right? So this you should remember. And if you talk about the energy stored in the inductor will be half L I square. So these formulas you have to remember. Now let us see some of the illustration. A current in an inductor is given by 3t plus 8, where t is in seconds. The magnitude of the induced EMF produced in the inductor is 12 millivolt. So induced EMF is given as 12 into 10 raised to power minus 3 volts. And the current is also given, that is 3t plus 8. And we have to find the self-inductance. And we know that in case of an inductor, the EMF induced is minus L di by dt. So it can be written as minus L, and di by dt will be 3. The differentiation of I will be 3. And EMF induced is 12 into 10 raised to power minus 3. So if you take only the magnitude, we can say L comes out to be 4 into 10 raised to power minus 3 Henry, which is 4 millihenry. So 4 is the answer. Now let us see the next question. In a coil, the current changes from minus 2 to plus 2 in 0.2 seconds and induces an EMF of 0.1 volt, the self-inductance of the coil. So again, we can use the same concept. Induced EMF will be minus L di by dt, and in this case induced EMF is 0.1 volt minus L, and di by dt can be written as delta I by delta t. So minus L, final current is 2, initial current is minus 2, divided by 0.2. So this comes out to be minus L times 4 upon 0.2, which is nothing but minus 20L. So if you take the magnitude on both sides, so 0.1 comes out to be 20 times L. So L will be 5 into 10 raised to power minus 3 Henry, which is 5 millihenry. So option 3 is the right answer. Now let us see the next problem type, and it is based on LR circuit with DC source. So suppose if we have a inductor which is connected with a resistor, and there is a battery, and there is a switch. So this is inductor, inductance is L, resistance is R, and the voltage EMF of the battery is E. Now when we close this switch at t equals to 0, then the current in this circuit will increase. So we can say E by R times 1 minus e raised to power minus RT by L, right? So that is the formula for current. And in steady state, when t tends to infinity, current will tends to E by R. And when we just close the switch at t, just when we close the switch, the current will be 0. So this you have to remember. in case of LR circuits. So let us see a question based on this. For the given circuit, the current through the battery of 6 volt just after closing the switch. So when we just close the switch, right, in that case, the inductor will behave like a open switch, right? Because there will be no current in the inductor. So we can say the circuit will look like this. So there is a resistor of 2 ohms and there is a battery resistor, and this inductor is behaving like a open switch. This is 2 ohms, 2 ohms, 4 ohms, right? So what we can say, if there is some current supplied by the battery, it will flow only through 2 ohms and this 4 ohm resistor. And by KVL, if you apply KVL in this loop, we can say the current will be V by the total resistance, which is 6 ohms. So this comes out to be 1 ampere. So we have to find the current supplied by the battery just after closing the switch. It will be 1 ampere. Okay, as per the figure, if di by dt is minus 1 ampere per second, then the value of VAB, so we have to find the potential difference between A and B, and the current is going in the left direction, and we have given the current is decreasing. Since the current is decreasing, then the left side of the inductor will be at high potential and right side will be at low potential. Now if you're going from A to B, so VA, so if I go in the direction of the current across the resistor, there will be a decrease in potential. So minus 12 times 2. So 12 is the resistance, 2 is the current. Then from negative to positive, that will be plus 6 times the rate of change of current, which is 1. And then from positive to negative, so there is a decrease in potential of 12. And we have reached B. So we have to find VA minus VB. So that will be 24 plus 12 minus 6. So that will be 30. So 30 volt is the answer, right? Now let us say the next problem type, and it is based on mutual induction. So what do you mean by that? If there are two coils, this is coil A and this is coil B. And if we set up some current in the coil A, that is the current is I1, right? So the flux linked with the coil 2, so this is coil 1 and this is coil 2. So there will be some magnetic field lines which will be linked with the coil 2. So the flux linked with coil 2 due to the current which we have set up in the coil 1 will be proportional to the current in coil 1. And the constant of proportionality is defined as the mutual inductance. And what is right? So from this we can find the mutual inductance, which is phi2 divided by I1. Similarly, we can also write this as phi1 divided by I2. And suppose if we want to find the induced EMF in the coil 2, so induced EMF in the coil 2 will be minus of d phi 2 by dt, which will be minus m di1 by dt. Similarly, EMF induced in the coil 1 will be minus m di2 by dt. Okay, now let us see some question based on this concept. Two coils having mutual inductance 0.002 Henry, and the current changes in the first coil according to the relation I equals to I naught sine omega t, where I naught is 5 ampere, omega is 50 pi radians per second. The maximum value of the EMF in the second coil is pi by alpha volt, the value of alpha. So the maximum value, so EMF induced in the second coil will be minus m di1 by dt, and I1 is given as I naught sine omega t. So if we differentiate this, we will get I naught omega cos omega t, where m is constant. So if I want to maximize the EMF induced in the second coil, you have to maximize the rate of change of current. So the maximum value di1 by dt will be nothing but I naught times omega, because the maximum value of cosine function is 1. So I naught is given as 5, omega is given as 50 pi, so this comes out to be 250 pi. So the maximum value E2 max will be m times, which is 2 into 10 raised to power minus 3 the maximum value of the rate of change of current, which is 250 pi. So it comes out to be 500 pi times 10 raised to power minus 3, which can be written as 0.5 pi or pi by 2. So pi by 2 volt is the maximum EMF induced EMF that can be induced in the coil 2. So alpha will be 2. So 2 is the answer of this question. Right, so let us see the next question. A small square loop of wire of side L is placed inside a large square loop of wire of side capital L. So here we have given a large square loop and the side is given as L, and there is a small square loop which is placed at the center and its side is given as small l. Okay, so the loops are coplanar and their centers coincides. The value of the mutual inductance of the system is root x times 10 raised to the power minus 7, and we have to find the value of x. So in this case, what we're going to do, we'll set up current in the outer loop and we'll find the flux through the inner loop. So let me call this loop as 1, this one as 2. So we can say phi 2 will be m times I1. Now what is phi 2? So phi 2 will be B1, that is the magnetic field produced by the outer loop at the location of the loop 2. So it will be B1 times, number of turns will be 1 only, times the area of 2. So that will be m times I1. So B1 will be what? So we know how to find the magnetic field by a square loop, no? So here what we have to do, that we have studied in magnetism. So let us find the magnetic field by one of the sides. So that will be mu naught I1 divided by 4 pi d, and d is the perpendicular distance, which is nothing but L by 2, times 2 times the sine theta, and theta will be 45 degree. So sine 45 degree. Now you have to multiply this with 4. So this is the magnetic field B1. So let us simplify this. So this can be written as 4 will get cancelled out, and mu naught will be 4 pi into 10 raised to power minus 7 times I1 divided by pi times L times 4 by root 2. So this pi will get cancelled out. So we have 2 root 2. So this will be 4, na? Let me correct this. It comes out to be, if I take this root, or if I rationalize this, so this will give us 2. So it will be 8 root 2. So 8 root 2 times 10 raised to power minus 7 times I1 by L. So that is B1. So let us put the value here. So 8 root 2 times 10 raised to power minus 7 divided by L times I1, and A2 in this case will be small l square, and it is equals to m times I1. So this I1 will get cancelled out, and we have given capital L is equals to L square. So let us remove this. So it comes out to be root of 128 into 10 raised to power minus 7. So x comes out to be 128, right? So let us see the next question. Two conducting circular loops A and B are placed in the same plane with their centers coinciding as shown in the figure. The mutual inductance between them. So again, in this case, B is very large in comparison to A. So we're going to consider current in the outer loop. Let me call this as I1, and or we can say this is our loop number 1 and this is loop number 2. So the mutual inductance will be flux through the loop 2 divided by the current in the loop 1. So flux will be magnetic field produced by the outer loop at the center, which will be mu naught I1 divided by 2 times B multiplied with the area of the inner loop, which is pi A square divided by I1. So this will give us mu naught times pi A square divided by 2B. So if you look at the option 4, that is the right answer. So now let us say the next problem type, and it is based on the series and the parallel combination of inductor. So first let us see the series combination. So suppose we have two solenoids or two inductors, and the windings are in the same order, same sense basically, right? So they have winding in the same sense. What do I mean by that? The current is also in the same direction. So if you look at it from the left side, the current will be clockwise in both the solenoids. L1 and L2 are the self-inductances for these two coils or two inductors, and let us say M is the mutual inductance between them. So in this case, the equivalent, if I want to replace this two inductor with a single inductor, so L equivalent will be given as L1 plus L2 plus 2M. But suppose if we have two solenoids or two inductors, but the current is in opposite direction. So this is the first inductor and this is the second inductor. So if this is the direction of the current, can you see now that the current is in the opposite direction? So if you look at it from the left side, in the first inductor the current is clockwise, and in the second inductor the current is counterclockwise. So this will be L2. So in this case the equivalent inductance will be L1 plus L2 minus 2 times M. And if you talk about the parallel combination, usually in JEE Mains they will mention that the mutual induction you can ignore. So in that case, if there are two inductors which are connected in parallel, if this is L1 and this is L2, then L equivalent will be L1 L2 upon L1 plus L2. Now let us see the question based on this concept. So two coils of self-inductance L1 and L2 are connected in series combination having mutual inductance of the coil as M. The equivalent self-inductance of the combination is, right? So if you look at this, these two coils, they are arranged such that their current, their winding are in reverse order. But if you look at the current, this current is entering from the other side. So we can say in the first case, in this particular case, let me draw here. If this is the core and this is the first solenoid, and let us say this is the second solenoid or second inductor. Right, so there is a current like this clockwise, and in the other solenoid the current is coming from the other side. Can you see? Now the current are in the opposite direction. So this is the case. This is the second case. So in second case the equivalent inductance is L1 plus L2 minus 2M. So in this case the answer would be option D. So that you have to keep in your mind. Now let us see the next problem type, and it is based on the peak value, average value, and the RMS value of the alternating current and voltage. So let us see. So if you talk about the alternating current, it can be given as I naught sine omega t. And if I want to find the average value of this, so the peak value is I naught. And if you want to find the average value, so average value of I will be integral I naught sine omega t dt from 0 to capital T divided by t minus 0. So that is the average value for one complete cycle, and for half cycle this will become t by 2 and this will become t by 2, and it comes out to be 2 I naught by pi for half cycle, and for full cycle the average value will be 0. Okay, and if you talk about the RMS value, it is nothing but root of integral I naught square sine square omega t times dt divided by t minus 0 from 0 to t. So this will give us the RMS value, which is root mean squared current. And for a sine function, RMS value is peak value divided by root 2 for a complete cycle or for a long interval of time. So these values you should remember. So let us see a question. An alternating voltage which is 220 times sine 100 pi t is applied to a purely resistive load of 50 ohms. The time taken for the current to rise from half of the peak value to the peak value. So we have given V, which is 220 sine 100 pi t. So in this case we can say the time period is 2 pi by omega, and omega is 100 pi. So, okay, so this is 100 pi. So which comes out to be 1 by 50, right? Now if I draw the graph, here we have voltage and this is the time. So it will be a sine curve. Now the time from 0 to maximum value. So this time will be nothing but 1/4 of the time period. So this time is 1 by 200 seconds. But we have to find the time from half of the peak value to the peak value. So half will be somewhere here, and this time interval we have to calculate. Okay, so let us see what is the value of t when voltage is half of the peak value. So this is the peak value. So when V is 110, we can say it will be 220 sine 100 pi t. So it will give us 1 by 2 on the left hand side. So 1 by 2 is equals to sine 100 pi t. So we can say 100 pi t is nothing but pi by 6, because sine pi by 6 is 1 by 2. So from this t comes out to be 1 by 600 seconds. So we can say the current so voltage from 0 to 110 will take how much time? 1 by 600 seconds. And from 0 to maximum or 0 to peak value, it will take 1 by 200 seconds. So we can say 1 by 200 minus 1 by 600 will be the answer. So that will be 2 by 600, which is 1 by 300. So we can say it will be 3.3 milliseconds. So option 2 is the right answer. Right, so let us see this question. An alternating current at any instant is given by I equals to 6 plus root 56 sine 100 pi t plus pi by 3. So we have to find the RMS value of the current. So when we have given a graph or when we have given a function, so how we can do the RMS value? First we have to square it. So let us square this, right? So it will be 36 plus 56 sine square 100 pi t plus pi by 3 plus 2 times 6 times root 56 sine 100 pi t plus pi by 3. Now what you have to do? You have to take the average. So the average of all the terms. So 56 is constant, so we have to find the average of sine square. Since 2 times 6 times root 56 is constant, so we have to find the average of sine function. So the average value of a sine square function over long interval of time is 1 by 2, and the average value of a sine function over a long period of time will be 0. So we can say the average value of I square function will be 36 plus 56 times 1 by 2 plus 2 times 6 times root 56 times 0. So this comes out to be 36 plus 28, which will be 64. Now what we have to do? You have to take the square root of this. So if you take the square root, this will be the RMS current, IRMS, which will be 8 ampere. So 8 is the answer of this question. Right, so let us see the next question. An alternating current voltage which is 110 root 2 sine 100 t volt is applied to a capacitor of 2 microfarad. The RMS value of the current in the circuit. Right, so here we have given a capacitor, and in case of a purely capacitive circuit, the capacitive reactance is 1 by omega c, which is 1 by 100 times 2 into 10 raised per minus 6. So that comes out to be 10,000 by 2, which is 5,000. So 5,000 ohms we can say is the resistance of this circuit. And if you want to find the IRMS, that will be ERMS divided by the capacitive reactance or the resistance of this circuit. So ERMS will be what? So this is the peak value of the voltage. So it will be E naught. So ERMS will be E naught by 2. E naught by root 2, sorry. So we can write this as 110 root 2 by root 2 divided by XC. XC is 5000. So this will get cancelled out. 0 will get cancelled out. So we can write this as 22 by 10,000, which is nothing but 22 milliampere. So 22 is the answer of this question. Right, so let us see next question. A parallel plate capacitor has a capacitance 200 picofarad. It is connected to 230 volt AC supply with an angular frequency of 300 radians per second. The RMS value of the conduction current in the circuit and the displacement current in the capacitor respectively. Okay, first let us find the RMS value of the conduction current. So we have given capacitor and we have given, so whenever we are given a voltage like this, it is the RMS value. So this will be ERMS. And this is omega. So capacitive reactance will be 1 by omega C, which is 1 upon 300 times C will be 200 picofarad, which is 10 raised to power 12. So this comes out to be 10 raised to power 8 divided by 6. So we have to find the RMS current. So RMS current will be ERMS divided by XC. So ERMS is 230 divided by 10 raised to power 8 times 6, right? So let us simplify this. This will be 138 into 10 raised to power 9, and we have to find in micro minus, sorry, this will be not 9, it will be minus 7, sorry. This will be minus 7. So it will be 13.8 microampere. So the conduction current will be 13.8 microampere, and if you know the concept of displacement current, which we will study in electromagnetic radiation, there we'll study the concept of displacement current, and displacement current comes out to be equal to the conduction current. So the answer will be option 4, right? Both are equal. Now the next problem type is based on the AC circuit. So let us see the different types of AC circuit that you should know. So first we have purely resistive. Then we have purely capacitive. And then purely inductive. So in purely resistive, there will be only a resistor in the circuit and there will be a AC source. So this will be E equals to E naught sine omega t, and the resistance is R. So here the peak current will be E naught by R, and the instantaneous current will be E naught by R sine omega t. And if you draw the phasor diagram, the peak current and the source voltage both are in the same phase. And in case of purely capacitive, which is having a capacitive reactance XC, which is 1 by omega C. So we can say in this case the peak current will be E naught by XC, and the instantaneous current will be, in case of a capacitive, purely capacitive circuit, current lead voltage by pi by 2. So this will be I naught sine omega t plus pi by 2. And in this case the current is leading the voltage by pi by 2. Now in case of a purely inductive circuit, where inductive reactance is omega times L, the peak current will be E naught by XL, and the instantaneous current will be I naught sine omega t minus pi by 2. So in case of a purely inductive circuit, current lags the voltage by pi by 2. So this will be, if this is E naught, then this will be I naught. So current is lagging the voltage by pi by 2. Now let us see RC circuit, right? See, RC AC circuit. So here we have a resistor and a capacitor, and this is the AC source L, and this will be C. Similarly, the capacitive reactance will be XC and inductive reactance will be XL. So in this case, if we plot the if I show the peak current, so peak current will be E naught divided by root of, okay, sorry, this is RC now, so let me change this. This will be resistor. So in this case, it will be XC square plus R square, right? And in this case, we can draw the phasor diagram. So if this is I naught, then this will be VR naught, and this will be, in this case, the current. Again, we have a RC circuit, so the current will lead. So here you can say this will be VC naught, right? And if I take the resultant of VC naught and VR naught, we'll get the E naught. So that will be E naught, and this will be the phase difference between the voltage and the current supplied by the AC source. So here tan phi comes out to be XC by R, and the peak current we have just seen, right? Similarly, in case of a RL circuit, the peak current will be A naught divided by root of XL square plus R square, and if and tan phi will be XL by R. And in case of a LCR circuit, I naught will be given as E naught divided by root of XL minus XC square plus R square, and tan phi will be given as modulus of XL minus XC divided by R. Okay, so this we have to remember. And if you talk about the power dissipation, so average power dissipation will be given as dot product of ERMS and IRMS, or this can be written as ERMS IRMS times cos phi, where phi is the phase difference between I naught and E naught. And this can also be written as ERMS square by impedance times cos phi, or we can also write this as IRMS square times R. So these values you have to remember. And this cos phi is known as the power factor. So power factor is cos phi, and wattless current is defined as IRMS times sin phi, and wattful current will be IRMS times cos phi. Okay, right. So let us see the questions based on these formulas. So we have given a series LCR circuit of L equals to 100 by pi millihenry, and capacitance is 10 raised to the minus 3 by pi farad, and the resistance is 10 ohms, is connected across an AC source of 220 volt 50 hertz supply. So this 220 is the ERMS and 50 hertz is the frequency. So the power factor of the circuit. Okay, so we know that power factor, which is cos phi, will be given as R by Z, where Z is the impedance, R is the resistance of the circuit. So in this case, we have given frequency. So from the frequency, we can find angular frequency. So omega will be 2 pi f, and f is 50, so this will be 100 pi second inverse. And if you want to find the power factor, we need to find the value of impedance, and impedance is given as root of, in this case we have LCR circuit, so this will be XL minus XC square plus R square. So let us find the value of XL and XC. So XL will be omega times L. So omega is given as 100 pi. And inductance, self-inductance is given as 100 upon pi millihenry. So from this, we will get 10 ohms. Now if you want to find capacitive reactance, it will be 1 by omega C, which will be 1 by 100 pi, and C is given as 10 raised to power minus 3 by pi. So from this, it comes out to be 10 ohms. So XL and XC both are equal. So the impedance will be nothing but the resistance. So since it is resistance, so we can say cos phi will be 1. So answer will be 1 for this question. Right, so now let us see the next question. So when a coil is connected to 20 volt DC supply, it draws a current of 5 ampere. When it is connected across a 20 volt 50 hertz AC supply, it draws a current of 4 ampere. The self-inductance of the coil is in millihenry. Right, so in a DC circuit, so this is 20 volt and there is an inductor. And we have given some steady state current which is 5 ampere. So we have a finite current. So it means this inductor must be having some resistance, right? So I'm showing a resistance also. Let us say this is R. And the inductance, self-inductance is L. And the steady state current is 5 ampere. So by Ohm's law, we can say I will be V by R in this case. And resistance of this inductor will be 20 by 5 ampere, so that will be 4 ohms. Now we know the resistance. Now we are connecting this inductor to a AC source. So there is an inductor and it has some resistance 4 ohms, and in a self-inductance we have to calculate, and it is connected with an AC source, and we know the ERMS. So this 20 volt is the ERMS value, and this is the frequency. So 220 volt times this will be 50 hertz. And now in this case the current is 4 ampere and it's a LR circuit. So in LR circuit the RMS current is defined as ERMS divided by root of XL square plus R square. Now let us substitute the values. ERMS is 20 and let us find the value of XL first. So XL will be omega times L. Omega will be 100 pi because frequency is 50 hertz, and L we have to calculate, right? So this will be 100 pi times L square plus R square. R square will be 16, so root of that. And this is given as 4 amperes. So this will give us 5. So let us square on both sides. So we'll get 25 equals to 100 pi L square plus 16. So this will give us 9. Root of 9 will be 100 by L. So L comes out to be 3 upon 100 pi. And pi we have to take as 3. So this comes out to be 1 by 100. Or I can write this as 10 millihenry. So 10 is the answer of this question. Right, so let us see the next question. In a AC circuit, the voltage and current across current are given by 100 sine 100t, that is the voltage, and the current is 100 sine 100t plus pi by 3 milliampere. So we have to find the average power dissipated in one cycle. So average power is, since current is given and voltage is given, so we can use VRMS IRMS times cos phi, right? Where phi is the cos phi is the power factor and phi is the phase difference between the voltage and the current. So VRMS, this is the peak value of the voltage. So VRMS will be 100 by root 2. This is the peak value of the current. So IRMS current will be 100 by root 2. And this is the phase difference pi by 3. So cos pi by 3 is 1 by 2. So we got 10,000 divided by 4. So this comes out to be 2500, and that will be 2.5 kilowatt. Oh, sorry, the current is in milli, na? So it should be this times 10 raised per minus 3. So 10 raised per minus 3. So that will be 2.5, not just 2.5. 2.5 watt. So option 3 is the right answer. Now let us see the next question. A series LR circuit connected with an AC source, which is 25 sine 1000 T volts, has a power factor of 1 by root 2. If the source of EMF is changed to 20 sine 2000 T, the new power factor. So power factor is defined as R by Z, right? And it's a LR circuit. So in LR circuit, we can say it can be written as R divided by XL square plus R square root of that, and this is given as 1 by root 2. So from this, if I square on both sides, we'll get 2R square is equals to XL square plus R square, and XL comes out to be R. Now if the source of EMF is changed to 20 sine 2000 T, now we are changing the source. Due to that, the angular frequency is also changing, right? Earlier it was 1000, now it has become 2000. And we know that the inductive reactance is omega times L. As we double so the frequency is getting doubled, so XL will also get doubled. So so the new XL will be 2R. Now if you use this value, what is the power factor? Resistance is not changing, so the new power factor will be R by root of XL prime square plus R square. So that will be R divided by root of 5R square. So that will be 1 by root 5. So option 3 is the right answer. Now let us see the next question. An AC voltage which is 20 sine 200 pi t is applied to a series LCR circuit which drives a current of 10 sine 200 pi t plus pi by 3, the average power dissipation. So we have given V naught, which is 20 volts. I naught is given as 10 ampere, and the phase difference is given as pi by 3. So we can say, we can use this formula. So VRMS IRMS times cos phi will give us the average power dissipation. So this will be 20 by root 2, IRMS will be 10 by root 2, and cos pi by 3 is 1 by 2. So this will give us 50 watt, right? So option 4 is the right answer. So in an AC circuit, the instantaneous current is 0 when the instantaneous voltage is maximum. So what does it mean? There is a phase difference of pi by 2 in voltage and the current. In this case, the source may be connected to. And when do we have pi by 2 as the phase difference? It can happen in pure inductor, it can happen in pure capacitor, or the combination of inductor and capacitor, right? In case of pure resistor, there will be 0, right? Power factor will be, you can say cos phi will be 1, or the phase difference will be 0. So if you look at the option A, B, D, so option 4 is the right answer. So when a DC voltage of 100 volt is applied to an inductor, a DC current of 5 ampere flows through it. Again, since we have given a finite current in the inductor, it means the inductor must be having some resistance. So in this case, if I draw the circuit, so we have 100 volt and there is an inductor which is having some internal resistance of R. And the steady state current will be E by R, so that will be 100 by R, and the current is 5. So R comes out to be 20 ohms. So when an AC voltage of 200 volt peak, this is the peak value, right? This will be E naught, is connected to inductor, its inductive reactance found to be 20 root 3 ohms. So XL is 20 root 3. So we have to find the power dissipation. So XL is given. So from this, E naught is given. So we can use, so the average power formula. So we have E RMS square by Z times cos phi, right? So we can use this formula. And ERMS in this case will be 200 by root 2. And impedance. So if I want to find the impedance, it is LR circuit. So XL square plus R square. And XL, we have just XL is 20 root 3, so that will be 400 times 3, that will be 1200, plus R square will be 400. So this comes out to be 40. So impedance is 40, and cos phi will be R by Z, and resistance is 20, and impedance will be 40, so that will be 1 by 2. So we got value of cos phi, we know what is ERMS, we know what is impedance. Now we can find the average power dissipation. So ERMS is 200 by root 2, and impedance is 40, and cos phi is 1 by 2. So let us simplify this. This is 4 into 10 raised to power 4 divided by 4 into 40. So this comes out to be 1 by 4 into 10 raised to power 3, and this will be 250 watt. So 250 is the answer of this question. Now let us see the next problem. A coil of negligible resistance is connected in series with 90 ohms resistor, and the AC source is 120 volts and 60 hertz. So this is the RMS value, and this is the frequency. Now we have LR circuit. So there is a coil which is connected with a resistor, and this coil is ideal. It has no resistance, and it is connected with an AC source. So let us take this as L, and this is 90 ohms, and this is 120 volt, 60 hertz. A voltmeter of 36 volt reads 36 volts across the resistor. Now this reading will be the RMS voltage, right? So across the resistor there is a voltmeter which is measuring RMS value, which is given as 36. So 36 is nothing but IRMS times the resistance, which is 90. So IRMS will be 6 by 15, or you can say 2 by 5. So 0.4 ampere is the RMS current in the circuit, and we have to find the inductance of the coil. So we have given ERMS, we have given frequency, so we can use so voltage is given, and we have to find the inductance. Okay, right. So XL will be omega, that will be 120 pi times L. L is not given, but we know what is the RMS current. So we can say IRMS can also be written as ERMS divided by impedance, and the impedance will be root of XL square plus R square. Now let us substitute the value in this. So we have 2 by 5 times root of XL square plus R square, that will be 90 square, equals to ERMS, which is 120. Now let us simplify this. So this will be 60. Now let us square on both sides. So we have XL square plus 90 square, that will be 300 square. So XL square comes out to be 90,000 minus 8100, right? Now from this we have to find the self inductance. So it will be 120 pi square of that will be L square. So it will be 90. Let me just simplify that. So 900 minus 81, so that will be 819, right? So that will be 81,900. So 120 pi L root of this. So L comes out to be root of 81,900 divided by 120 pi. So if I calculate the value of this, let me quickly check. So that will be root of 81,900. So which comes out to be so this value will be 286, nearly 286 divided by 120 divided by 3.14. So we are getting this value nearly equals to 0.76 Henry, right? So option 2 is the right answer. Okay, now let us see the next problem. So here we have given a list, two columns, and we have to match the column, right? So in the list one, we have A is purely capacitive circuit. So in purely capacitive circuit, and we have given phasor diagrams in the second list. So in purely capacitive circuit, current leads the voltage by pi by 2. So we can say A corresponds to 1, where current is leading. So A corresponds to 1. So it means option 2 and option 3 are incorrect. In purely inductive circuit, current lags the voltage by pi by 2. So B corresponds to 4. And in LCR circuit, in resonance, uh, the phase difference will be 0. Current will be in this, there will be no phase difference between the current and the voltage. So C corresponds to 2. And in LCR circuit, yes, there can be some finite phase difference. So phi. So D is 3. So let us compare A1, B4, C2 and D3. So option 1 is the right answer. Okay, let us see the next question. For a given series LCR circuit, it is found that maximum current is drawn when the value of the variable capacitance is 25 nanofarad. So maximum current happens when we have resonance. And what is resonance? When impedance will become equals to resistance, or you can say XL is equals to XC. So when the reactance of capacitive reactance is equals to the inductive reactance, and capacitance is given to us. If the resistance is 200 ohms and 100 millihenry inductor is being used in the circuit, the frequency of the AC source. Now from this, XL can be written as omega frequency omega times L, and L is 100 milli, and XC can be written as 1 by omega C, and C is 25 into 10 raised to power minus 9. Now from this, omega square will be 1 by 25 times 10 raised to power minus 10. Now if you take the square root on both sides, so omega comes out to be 1 by 5 times 10 raised to power minus 5. Or this can be written as 100 times 10 raised to power 3 divided by 5, which will be uh, yeah, so this comes out to be pi term. Okay, right. So this is the angular frequency. So this comes out to be 20 into 10 raised to power 3 second inverse. But we have to find the frequency. So frequency will be omega upon 2 pi. So omega is 20 into 10 raised to power 3 upon 2 pi. So this can be written as 10 into 10 raised to power 3 divided by pi, right? So they have said take pi square as 10. So this can be written as 10 pi divided by pi square into 10 raised to power 3. So this will give us pi into 10 raised to power 3 hertz. Okay, but in the key the answer is given as this. Instead of pi, the answer is given as 10, but the actual answer should be pi, or you can say the if it is integer type, so the answer will be 3, right? So 3 times 10 raised to power 3 hertz. So that should be the answer of this question, right? So let us see the next problem. Given below are two statements. Statement 1 is in LCR circuit, current is maximum at resonance, so that is fine. So in statement 2, current is in purely resistive circuit can never be less than that in the LCR circuit when connected to the same voltage source, right? So in case of a purely resistive, the current IRMS can be written as ERMS by Z, and in LCR circuit IRMS will be ERMS divided by root of XL minus XC square plus R square. Now can you see in case of LCR circuit, the impedance will always be greater than the resistance. So that's why the current will always be less than the current in the purely resistive circuits. So statement 2 is also correct. So in the light of the above statement, we have to check which options are correct. So both the statement 1 and 2 are true, so option 3 is the right answer. Okay, so we have given a bulb and a capacitor are connected in series across a AC supply. A dielectric is then placed between the plates of the capacitor, the glow of the bulb. So the glow of the bulb will depend upon the current which is passing through the bulb. So greater the current, more will be the brightness. So if we are inserting a dielectric, the capacitance will increase, and we know that the capacitive reactance is 1 by omega C. So as C increases, XC decreases. So if XC decreases, the impedance in this case, the bulb, we can treat bulb as a resistor. So it's a RC circuit. So it will be XC square plus R square. As XC decreases, impedance will also decrease. And we know that IRMS is equals to ERMS divided by impedance. So as impedance is decreasing, current will increase. So the glow will increase. So option 1 is the right answer. Now let's see this question. An AC source is connected in a given LCR circuit. The RMS potential difference across the capacitor of 20 microfarad. So RMS potential difference. So VC RMS can be written as IRMS times capacitive reactance. And in this circuit, we have given peak voltage, angular frequency is also given. So first let us find the impedance of this circuit. So that will be root of XL minus XC square plus R square. So what is XL? So XL will be omega times L, and omega is given as 100. L is given as 1, so that will be 100 ohms. And XC will be 1 by omega C, so that will be 1 by 100, and C is given as 20 microfarad. So this will be 100 times 100 by 20, so it will be 500. Okay, so this will be 500. So we can say impedance will be root of 400 square plus resistance is 300. So it comes out to be 500. So the impedance of this circuit will be 500 ohms. And so if you want to find the IRMS current, so that will be ERMS divided by impedance, and ERMS will be 50 root 2 by root 2, right? So because peak voltage is 50 root 2 divided by impedance, which is 500. So this comes out to be 1 by 10. So we know what is IRMS. So this can be written as 1 by 10, and XC is 500. So this comes out to be 50 volts. So 50 is the answer of this question. Right, so in this problem, a series LCR circuit is subjected to an AC voltage of 200 volt and 50 hertz. This is RMS voltage and this is the frequency. If the voltage across the inductance is also given 10 millihenry, is 31.4 volts, then the current in the circuit. So we have given VL RMS, right? Whenever a voltage is given something like that, so it is always the RMS value, not the peak value. So it will be IRMS times XL. And frequency, angular frequency is 100 pi. And this is given as 31.4. IRMS will be, it's a LCR circuit now, and we have to find the current. So IRMS and XL will be omega. Omega is 100 pi times L. L is 10 millihenry. Milli can be written as 10 raised to power minus 3. Right, so from this we have to find the RMS value, IRMS. So this pi is 3.14. So this will give us 10 here. So IRMS will be this will be 10,000. So we are getting IRMS as 10. So 10 ampere is the answer of this question. Okay, let's see next question. A capacitor of reactance 4 root 3. So this is XC and a resistance 4 ohms are connected in series with an AC source of peak voltage 8 root 2. So that will be E naught, let us say. The power dissipation in the circuit. So we want to find the power dissipation, or XL, XCR, and E naught is given to us. So first let us find the impedance. So impedance will be root of XC square plus R square. So that will be 16 times 3, 48 plus 16. So this comes out to be root of 64. So that will be 8. So 8 ohms is the impedance, and we know E naught. So here we can use E RMS square by Z cos phi. So that will be the average power dissipation, and cos phi can be written as R by Z. So it will be E RMS square R by Z square. So let us put the value in this formula. So E RMS will be 8 root 2 by root 2 square of that times R is 4 divided by impedance square. Impedance is 8, so that will be 64. So this 8 will get cancelled out, and this root 2 will get cancelled root 2, so we are getting 4 watt. So 4 is the answer of this question. Right, so now let us see the next problem type, and it is based on the resonance in LCR circuit, and we know that in LCR circuit IRMS is ERMS divided by root of XL minus XC square plus R square. So at resonance the current will attain its maximum value. So we can say XL will be equals to XC at resonance, and from this the resonating frequency, the frequency at which we are getting resonance, will be 1 by root LC. So this concept we have to remember, and at this particular frequency the IRMS current will be maximum, and that will be ERMS divided by R. Okay, let us see the question. So in series LCR, the capacitance is changed from C to 4C. To keep the resonance frequency unchanged, the new inductance should be. Right, so we know that the resonating frequency, angular frequency, is 1 by root LC, or we can say the frequency will be 1 by 2 pi root LC. So the frequency depends upon the product of LC. So as we are increasing capacitance by 4 times, the inductance should be reduced by the factor of 4. So the new L will be L by 4. So the new inductance should be reduced by L by 4. So basically you have to reduce inductance by 3 by 4. 3 by 4 times L. So option 3 is the right answer. A LCR circuit is at resonance for a capacitor C, inductance L, and the resistance R. Now the value of the resistance is halved, keeping all other parameters same. So R, we have made it half. The current amplitude at the resonance will be, so at resonance I naught will be E naught divided by R. So as we halve the resistance, the current will become double. So it should be option 4. Now the next problem type is based on LC oscillation. So what happens in this case? Let us see. So we have an inductor and there is a charged capacitor, and let us, there is a switch. So it has some positive charge, this plate is having some negative charge, and the initial charge is Q naught. right? So when we close this switch, then this capacitor will try to discharge. So earlier the energy was stored in the electric field between the plates of the capacitor. As this capacitor getting discharged, there will be a current in the circuit, and due to this current, now there will be some magnetic field associated with the inductor, and due to that magnetic field there will be some energy. So we can say in LC oscillation, the energy stored in the electric field in capacitor, uh, you can say it will be converted into the energy stored in the magnetic field in the inductor. Now this energy will keeps on oscillating, and this is known as LC oscillation. Now what you have to remember in this, the instantaneous charge will be Q naught, and that will be cos, and omega in this case will be 1 by root LC times T. Right, so this you have to remember. So that is the instantaneous charge on the capacitor, where Q naught is the initial charge on the capacitor. And if you want to find the current, we can differentiate that. So the current will be Q naught by root LC times sine 1 by root LC times T. Or we can also remember that instantaneous charge, or the current, instantaneous current will be given as 1 by root LC times root of, it will be Q naught square minus small q square, right? So these three formulas you have to remember. Okay. Now let us see a question based on this. A capacitor of capacitance 100 microfarad is charged to the potential of 12 volt and connected to 6.4 millihenry inductor. So that is L, and this is the initial potential difference of the capacitor. So the charge Q naught will be CV. So that will be 12 times 100 micro coulomb. So that will be 1200 microcoulomb. The maximum current in the circuit would be, so we know that current is given as Q naught by root LC sine 1 by root LC times T. Now by using this, the maximum value is nothing but Q naught by root LC. So Q naught is 1200 microcoulomb and root LC. So L is 6.4 into 10 raised to power minus 3, and C is 100 into 10 raised to power minus 6. So let us simplify this. So this will be 1200 into 10 raised to power minus 6, and in the denominator we can remove this decimal and we will get 64 into 10 raised to power minus 8. So that will be 1200 divided by 8 into 10 raised to power minus 4 times 10 raised to power minus 6. So this will be 10 raised to power minus 2 and 2, and this will be 300, which is 150 into 10 raised to power minus 2, which is 1.5. So 1.5 ampere is the maximum current. So option 2 is the right answer. Now the next concept is based on the AC generator. So here what concept we're going to use. Suppose we have a coil and it is placed in uniform magnetic field, and we are rotating this coil about its diameter with a constant angular frequency, or you can say angular velocity omega. N is the number of turns, A is the area of this coil. So the instantaneous flux will be given as NBA cos omega t. So the induced EMF will be given as NBA omega sin omega t, and the induced current will be NBA omega by R, where R is the resistance of this coil, sin omega t. Okay, so this you have to remember in AC generator. Now let us see a question based on this. A coil of 200 turns and area zero point 0.2 square meter is rotated at half a revolution per second. So half revolution corresponds to 2 pi radians. So that will be pi radians per second. That is omega. and is placed in a uniform magnetic field of 0.01 Tesla perpendicular to the axis of the rotation of the coil. The maximum voltage generated in the coil is 2 pi by beta volt. What is the value of beta? So maximum voltage is the EMF value, right? So if you look at this relation, it is NBA omega. So the maximum voltage will be NBA omega, and this is given as 2 pi by beta. So let us simplify this. So N is 200, magnetic field is given as 0.01, and area is given as 0.20, and angular velocity is pi. So that will be 2 pi by beta. So this pi will get cancelled out, and this will give us 2 here. So it comes out to be, and this 2 will get cancelled out with this 2. So we're getting 0.2 equals to 1 by beta. So beta will be 5. Right? So 5 is the answer of this question. Now the last problem type that we have to discuss is transformer. So in transformer, what you have to remember, there are two windings. So here we have primary winding. So let us say NP is the is the number of turns in the primary winding, and EP is the EMF induced in the primary winding, and IP is the current. Similarly, in the secondary winding, NS is the are the number of turns, ES is the EMF induced, and IS is the current. So in case of an ideal transformer, EP by ES will be NP by NS, and EP by ES is IS by IP, right? So that you have to remember. And in case of a real transformer, in real transformer there is a efficiency term which is defined as percentage efficiency will be power output upon power input times 100, right? So that is the percentage efficiency. And we can say power output is power input minus losses in the power, right? Now let us say the question based on this. A transformer has an efficiency of 80% and works at 10 volts and 4 kilowatt. The secondary voltage is 240. So this is the primary voltage. We can say this is EP and this is ES. Then the current in the secondary. So we have to find the current in secondary, and efficiency is given. So input power. So this is input power. So output power will be 80% of input power, because 80% is the efficiency. So that can be written as 0.8 times 4 into 10 raised to power 3 watt. So that will be 3200, right? So that is our output power. And output power can be written as IS times ES, right? And IS we have to calculate, and ES is given as 240. So, and this is 3200. So let us simplify this. So this comes out to be 3, and this will be 4. So it will be 4 by 3. Sorry, 40. Sorry, it's 40 by 3 is the answer. So that will be 13.33 ampere. So option 2 is the right answer. Now let us see this question. The primary coil of a transformer is connected to 220 volt AC, and primary and the secondary turns of the transformers are 110. So here we have 100 turns, here we have 10 turns. Secondary coil of transformer is connected to two series resistors shown in the figure. The output voltage is. So we have to find the voltage V0 which is across the 7 kilo ohms resistor. Right. So here, since this is 220, we can say the voltage across the secondary will be 220 times 10 by 100, right? So which will be 22 volts. Now this 22 volts is appearing across this series combination of two resistors. So we can say, so we have two resistors which are in series, and across this we have a voltage of 22 volts. So this is 50 kilo ohms and this is 7 kilo. And we know that when the current is same in two resistors which are connected in series, then the potential will divide based on the resistance. So we can say the potential across 7 kilo ohm, let me call this as V0 only. So V0 will be 22 times 7 kilo divided by 7 kilo plus 15 kilo. So this comes out to be 22 times 7 divided by 22. So that will be 7 volts. So option 1 is the right answer. Now let us see this question. Primary side of the transformer is connected to 230 and 50 hertz supply. So this is ERMS, or you can say EP. This is turn ratio primary and secondary is this. So this will be NP and this will be NS. And the load resistance connected to the secondary side is 46 ohms, the power consumed in that. Okay, right. So in this case, we know that EP by ES is equals to NP by NS. So this can be written as 230 divided by ES will be 10 by 1. So ES comes out to be 23 volts. Now we know the voltage across the secondary winding, and we have given the load resistance. So if you want to find the power, that will be ES square divided by R, and R is 46. So this will be 23 times 23 divided by 46. So this will be 2, and it will be 11.5 watt. So option 3 is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.